Hello everyone, my name is Congjie, a PhD student at the University of Edinburgh. Today, I will present our work, Wafer-LLM, focusing on large language model inference at wafer scale. This is joint research by me, Yeqi, Pei, and Luo from the University of Edinburgh, and the Ziming, Jilong, Lingxiao, and Fan are from the Microsoft Research. Language model inference consists of prefill phase and the decode phase. Prefill phase mainly involves matrix multiplication, generating the first token and the initial KV cache. Decode phase primarily involves vector matrix multiplication and always dominates the most of inference overhead. For each new token, it requires loading the full model width and the KV cache, so meeting an extremely high memory bandwidth demand, such as decoding 10,000 tokens per second for DeepSeek R1 already needs 360 terabytes per second memory bandwidth with just one request. And this demand will keep growing, driven by the emerging application scenarios, such as test time scaling and agentic workflow, which will expect millions tokens per second per request. It's very huge. But now, a single course on-chip memory capacity and bandwidth is significantly insufficient for language model inference tasks. So today's AI system mostly rely on off-chip solutions like HBM and NVLink to scale, offering bandwidth in the tens of terabytes per second range. However, this kind of off-chip interconnect-based scale-out is constrained by communication latency and bandwidth, which limits overall cluster performance and still fails to provide sufficient memory bandwidth for language model inference. Recently, another promising approach has emerged, leveraging mesh-like network-on-chip architectures to interconnect millions AI-optimized cores on wafer scale. Shown as the right figure, there is tens of times bigger chip size than off-chip scaling method. The wafer scale integration can aggregate from tens to hundreds of more memory, compute power, and bandwidth. Imagine that to fit the entire rack scale computer into a single wafer. At the same time, this not-connected wafer-scale integration is complementary to existing off-chip scale-out approaches. For example, multiple Cerebrus WSE chips can be interconnected with petabyte-scale off-chip memory via its Swarm-X system and the Memory-X system. In fact, wafer-scale integration already had a history dating back to the 1980s. Jim Amda, the creator of Amda's law in parallel computing, shared similar insights that scale chip performance and reduce energy cost via wafer-scale integration. He raised $200 million to co-found Trilogy System, the first company to pursue wafer-scale integration as its core technology. This was a bold move during the economic downturn of the 1980s. Unfortunately, Trilogy System ultimately failed, not only due to the weak market demand at the time, but also because of the limitation in chip manufacturing and cost, which made it nearly impossible to achieve sufficient yield at that scale. But 40 years later, now, a lot of things have changed. First, market demand has changed. As we mentioned earlier, today's language model inference tasks require much higher memory bandwidth, and this trend will keep growing as AI continues to advance. Second, advances in chip fabrication enable hardware remapping to greatly improve chip availability. Smaller core size help localize defect, while redundant wiring allows the system to bypass defective cores. Third, remapping has become viable and cost-effective. Advanced process enables smaller, faster cores, which improve yield and make hardware remapping cheaper and more practical. TSMC also predicts that 3D stacking technologies based on CoWoS chip packaging will offer significantly greater compute and memory bandwidth in the near future, compared to other AI accelerators built using a 3-nanometer process. The wafer-scale chip delivers tens of thousands of times higher memory bandwidth, all within a single chip. More importantly, off-chip scaling only can rely on PCB or RDL to enable die-to-die connections, such as the GPU cluster interconnected via NVLink and IBRDMA, while wafer-scale chips employ a large-scale network on chip across the entire wafer. The on-wafer die-to-die interconnection take around several hundreds times higher bandwidth and memory access for efficiency advantages than that of off-chip. This means that if wafer-scale chip can be effectively utilized, they offer significant advantages in both performance and energy efficiency over today's mainstream AI accelerator. Thanks to the more advanced system on wafer performance, more and more companies are trying the wafer-scale chip, such as Airbus, Tesla, Perplexity, and Mixture. We want to ask that are language model system ready for wafer-scale chips? Existing work on off-chip scaling is not sufficient. Many works have been proposed to better utilize NVLink and RDMA-based interconnections, such as new network topology, new system, multi-dimensional parallelism, and communication operator tailored for language model workload. Other efforts include flash attention, page attention, and AI parallelism compilers, which are designed to make better use of multi-level off-chip shared memory hierarchies. However, when these approaches are applied to wafer-scale chips with large mesh topology nodes, they often fail to effectively leverage the hardware on the millions of cores level and suffer from severe communication bottlenecks. This raises an important question. What challenges arise when designing software for wafer-scale hardware? Plummer model is the answer. First, there are millions of cores on a single chip. Traditional systems typically handle hundreds of cores, but the wafer-scale architectures can scale parallelism to millions of cores. This massive scale demands entirely new parallelism strategies and framework to ensure efficient coordination and synchronization across these cores. Secondly, there is the issue of highly non-uniform latency. In wafer-scale chips, accessing neighboring cores might take as little as 1 cycle, whereas accessing distant cores could take 1,000 cycles, representing a 1 to 1,000 time latency difference. Therefore, existing shared memory or all-to-all communication schemes no longer surface, necessitating new communication methods aware of this latency variability, such as mesh-like communication patterns. Thirdly, constrained local memory poses significant challenges too. Each core at the wafer scale typically has limited local memory, often just hundreds of kilobytes to a few megabytes. This sharply contrasts with conventional coarse-grained memory method, requiring finer-grained, carefully optimized placement strategies to ensure optimal utilization. Finally, limited routing resources constrain communication flexibility. Each core supports only tens of routing entries due to area limitation, while existing approaches often require millions, shown by the red line. Once routing entries are exhausted, routing falls back to compute costs, like the yellow line, adding some latency. Future wafer-scale chips require routing strategies that stay within NOC to avoid software-level overhead. Based on these 4 observations, we propose the Plummer model to guide wafer-scale chip users in designing high-performance software for on-chip, large-scale distributed memory. According to the proposed Plummer model, we design WaferLLM, a LLM inference system with various hardware backends that conform to the Plummer model. This is the current system architecture of WaferLLM. We start from a language model chain point and apply Plummer-compliant parallelism strategies for prefill, decode, and KV cache management. These are paired with novel on-chip distributed operator, including our own MeshGEMM and MeshGEMV. We have deployed this on Cerebras WSE2 with ongoing work on WSE3. Powered by these core contributions, WaferLLM breaking a new world record with over 2,000 tokens per second per request. But due to the time constraint, today I will focus on the implementation details of decode parallelism, MeshGEMV, and KV cache management. For the prefill and the MeshGEMM, we just post the result here. Details, please refer to our paper. In the decode phase, MeshGEMM replicates the activation vector across devices and partitions the weight matrix along the output embedding dimension. The embedding dimension limits parallelism at a few thousand level, violating the P principle in Plummer. Compiler-based method ignore highly non-uniform latency in mesh topology, violating the L principle in Plummer. In contrast, WaferLLM decode design fully complies with Plummer. It both partitions and replicates the vector, enabling million-scale parallelism. It also uses distributed GEMV and pre-place the weight matrix to avoid the vector transpose overhead on the mesh topology. Vector matrix multiplication at on-chip large-scale distributed memory also poses challenges due to the all-reduced communication. For example, ring all-reduce requires each submatrix to be passed through every core in the same row or the column on the mesh topology core by core. Our MeshGEMV utilizes a novel K-tree all-reduce approach, dramatically reducing critical latency and routing overhead by a tree-based grouped parallel reduction. Importantly, our method can trade routing resources for lower critical path latency, achieving maximum utilization of available routing resource. Efficient KV cache management is also critical for high-performance language model inference. Traditional approaches shown on the left as existing concat update method often lead to skewed memory usage, where some core quickly become overloaded, causing out-of-memory situation and performance degradation, which violates the M principle in Plummer. To address this, WaferLLM employs a novel shift-based KV cache management specially designed for mesh-like distributed memory. This management avoids out-of-memory caused by skewed core usage, and the rebalance process is achieved just via data movement between the adjacent cores, which is fully Plummer compliant. We compare WaferLLM on Cerebras WSE2 with Jilong VRM on NVLink or IB-connected A100 GPU in performance and energy efficiency. These two hardwares use the same process node. As shown in the table, cross-device and node communication via off-chip connections significantly harms the scalability. When scaling from 1 GPU to 8 GPUs, improves per request throughput by around 3 times. But performance drops at 16 GPUs. At this point, the memory bandwidth gains from multi-node scaling are outweighed by the performance loss from cross-node InfiniBand communication. Even under best-case GPU scaling, with no limit on device count, WaferLLM on a single WSE2 chip delivers 10 times higher per request throughput, along with a roughly 2.2 times improvement in energy efficiency. WaferLLM is just the first step of our long journey. Many challenges remain. First, are there AI model architectures better suited for wafer-scale chips? Can we design coarse and large-scale interconnects that better match AI workload? And also, at the software level, can we build more effective abstractions for wafer-scale distributed memory? This work appreciates the hardware support by Edinburgh International Data Facility and Edinburgh Parallel Computing Center. You can scan the QR code, find WaferLLM's open source code. Thank you for listening. Questions are welcome.